Yes, 9 o'clock, time to start. Welcome to the Licentiate seminar of Natnael Demissie. The title of the thesis today is UV-based advanced oxidation process for nutrient stabilisation and organic micropollutant degradation in source-separated human urine. My name is Anders Hansson, appointed by the faculty to chair this session, also professor at the Department of Energy and Technology. And then I just also, of course, want to welcome the members of the evaluation committee. Professor Kai Udot from EAVAG in Switzerland, welcome. Dr. Johannes Järmacka from Tampere University in Finland, Tampere, welcome.
Thank you.
And then we hope that we also have Associate Professor Zeynep Gurol with us from KTH in Stockholm. Is she with us?
Yes, I'm here. Good morning.
Perfect. But then, of course, we also have our own Åke Nordberg as deputy in the evaluation group here. So if the digital system will close down again, we will have a walk-in. And the schedule for today is that we will present the thesis for 30 minutes or so.
Okay.
And then I leave the word to the evaluation committee for discussion. And after that, it's open for the audience, both here in place and perhaps also at the Zoom link to open up questions and discussions. After that, I will close this official session. Then there will be a closed session at our department, I think, and also assume that there will be something served for you when you are waiting for the decision. Then that was all the formality. But before you start, I just want to ask you: do you have any things that you want to add? Any errata list or something?
No.
Thanks.
Yeah, thank you so much.
And then, yeah, floor is yours.
Thank you so much. Thank you all for coming. I want to thank my supervisory committee as well as the reverse committee. Thank you for attending. I will start my presentation, and then here is the content of my presentation. I'll directly go to the background. People understood the value of waste since ages, and they used to fertilize their land as well as their agricultural farms using human excreta and wastewaters to utilize the nutrients residing in them. And such practice is believed to exercise for 1,000 years in China, and it's believed to start around 12 BC in Japan, as well as around 18th century in Sweden. Currently, there is an estimate that 360 billion metric cubic of wastewater is generated, and then out of this generation, only 60%, around 60% is collected, and then from this collected, only 50% is being treated. Urine, representing 1% the volumetric load of household wastewater, contains majority of the nutrients which are essential for plants. And separating the urine and recovering the nutrients not only lead us for the production of valuable fertilizer, but also it will help us to reduce the operational cost as well as the carbon dioxide emission in wastewater treatment plants. However, source separation of urine in large scale from urban settings and then transporting the urine to agricultural land faces a logistical challenge because urine contains around 95% water. Therefore, concentration of nutrients in the urine is necessary. And can concentrate the nutrients in the urine either from fresh urine or hydrolyzed urine, but for technologies aiming at recovering especially the nitrogen in the form of urea, are challenged by the presence of urease, which is ubiquitous in source separating toilets. Because this challenges the recovery of nitrogen acid hydrolyzes urea in the form of ammonia and bicarbonate, which the ammonia in the open system can leave in the form of gas, leading to nitrogen loss. Therefore, a pretreatment step where the urea nitrogen or the nutrients are stabilized is necessary. So the common method to stabilize the nutrients require chemical addition. We can add acids or bases, and such use of addition of chemicals in household settings sometimes might be risky when we use like sulfuric acid, for instance. Therefore, an alternative nutrient stabilization method is required. Furthermore, along with like when we collect the urine, substances of concern like pharmaceuticals are collected along with the urine, and then such pharmaceuticals might leave our body in the form of parent compound or as a metabolite. And when these compounds, unless they are contained, they might create an adverse effect for non-target organisms in aquatic ecosystems. So we can, for instance, there is an effect of feminizing fish, and then they can alter the predation of fishes in the aquatic environment, and they can even create or build antimicrobial resistance, which might be transferred to pathogenic organisms that might come back to us in some form or another. And such pharmaceuticals can even persist for long storage of urine, and they can also persist, reaching the final urine-derived fertilizer, and then we can find them up to milligram per kilogram of fertilizer. Therefore, this substance of concern or pharmaceuticals must be removed prior to concentrating the urine. So UV technology that we commonly found in the drinking water treatment plants has the potential to both inactivate the urease enzyme as well as degrade the pharmaceuticals of interest. And then it can do this job by photochemical methods where both the enzyme as well as the pharmaceuticals contain photosusceptible functional groups that can respond to UV light. For example, urease enzyme contains amino acid residues like histidine, cysteine, and tryptophan, and upon UV absorbance, these functional groups might change their structure or might lose their functional groups, which lead them to lose their enzymatic activity. And furthermore, when it comes to the degradation of compounds, they also have photosusceptible functional groups, but their degradation depends on their photochemical property, which is measured based on their molar absorption coefficient as well as their quantum yield. So through this, UV treatment can directly degrade as well as inactivate the urease enzyme. Furthermore, the UV treatment can degrade as well as inactivate the enzymes through indirect photolysis method, where reactive radicals like hydroxyl radicals are formed during UV treatment. So within this method, the combination of these methods, we can inactivate the urease enzyme as well as degrade pharmaceutical compounds in water or wastewater matrices. So saying this, previous research which is conducted for the inactivation of urease limit their study either in water or phosphate vapor solutions, and those which studied the degradation of compounds limit their study either in synthetic urine or water or wastewater matrices. And those which are conducted for the those investigated the degradation of compounds limits their study for few number of compounds at a time. Therefore, in this thesis, UV treatment is proposed as an alternative treatment for the stabilization of urease enzyme, as well as degradation of pharmaceuticals from source-separated urine. And we set our main objective to be to evaluate a UV system as an alternative nutrient stabilization, as well as pollutant reduction method for safe nutrient cycling of source-separated urine. And then in order to achieve this objective, we set our specific objectives to be to determine the effectiveness of UV treatment in the inactivation of urease enzyme, as well as in the degradation of micropollutants, as well as determining the amount of energy required to achieve this. And In order to meet the specific objective, we followed this method where urine is collected in sterile polyethylene cups from donors, and after that the urine is collected, pooled and mixed, after which 500 milligram per liter of urease is spiked, and then after that the spiked solution is subjected to UV treatment, after which the enzymatic activity is tracked with conductivity measurement. But beforehand, we made a standard curve relating total ammonium nitrogen with the conductivity, and then we used such standard curve to determine the residual enzymatic activity in the UV treated samples. And furthermore, this study also investigated the inactivation of urease enzyme in water as well as synthetic urine, and they were spiked with the same concentration of the enzyme, and then they will be subjected to the same treatment time with the UV, and then after that, urea will be spiked so that we will know how much of the residual enzymatic activity is left in the treated solutions. In the second study, where we investigated the degradation of pharmaceuticals, we follow the same methods for the collection, and then after collection, a cocktail of pharmaceuticals entailing more than 150 compounds representing 27 therapeutic classes like antibiotics, antidepressants, and beta blockers, and as such, they were spiked with the concentration of 60 microgram per liter. And then after that, they will be subjected to UV treatment, different level of UV treatment. After that, the pharmaceuticals were extracted, concentrated, and then finally measured through LC-MS. Going to the results. During investigation of urease inactivation in water and real urine matrices, for the UV controls, we found comparable enzymatic activity between synthetic urine as well as water matrices, where total ammonium nitrogen reached equilibrium within 2 hours of treatment, whereas it took around 4 hours of treatment in the urine. So the reduced activity for the urease enzyme in the urine might be attributed to the thiol containing compounds, as well as the heavy metals which are contained in the urine and then not present in the synthetic or wastewater matrices, which has the potential effect to reduce the enzymatic activity of urease. And when we come to the UV treatments, this UV treatment greatly affected the enzyme activity both in water as well as in synthetic urine, where the enzymatic activity reached below detection limit within 3.3 minutes of UV treatment. But when we come to the UV treatment of real urine, those samples which are subjected to UV treatment within less than 1 minute didn't have any significant difference with enzymatic activity compared to the control treatments. Whereas when we come to the UV treatment, samples receiving more than or around 71 minutes of UV treatment greatly altered the enzymatic activity, where the enzymatic activity was below detection limit after the treatment. But during UV treatment of real urine, since the urine contains urea, when we spiked the urease in the urine, there was urea hydrolysis during the UV treatment. And as you can see over here, this is the enzymatic activity inside the photoreactor, and then this is after the UV treatment, and the enzymatic activity is higher during inside the photoreactor, because inside the photoreactor the temperature reached around 35 degrees centigrade, which is higher compared to the temperature in the control experiments, which was around 22 degrees centigrade. So since it requires more UV treatment time to inactivate urease enzyme in the urine, we require more than 50-fold of higher energy compared to synthetic urine. Continuing to the other study where we investigated the degradation of pharmaceuticals in the urine, we started the experiment with more than 150 compounds representing different therapeutic groups. And we ended up reporting only 75 compounds because the rest of the compounds didn't pass the analytical criteria. And we found an average degradation of 99%, or they are like almost removed in the water solution. But for the urine solution, it was only 55%. And the degradation differs from compound to compound, even if they belong to the same therapeutic class. For example, amoxicillin from antibiotic group and then azithromycin from antibiotic group, they show different response towards UV treatment. Along with 55% reduction of organic micropollutants, we also removed 20% of the COD as well as around 20% oxidation of the urea. But the total nitrogen is not affected, even if the urea is somehow oxidized. Continuing to the kinetics of the pharmaceuticals degradation, we found three kind of degradation trends, where the first is persistent towards UV treatment, where you will see over here the concentration didn't change after the treatment. And the second type of trend that we observe is a moderate degradation kind of trend. And this we will see for the UV treated memantine in water solution and then UV treated sotalol in urine solution. And the third type of trend that we observed was fast degradation, where the spike concentration reached below detection limit within 1 minute of treatment. And in general, we got an average of T90 for the whole pharmaceutical, for the whole spike pharmaceuticals of less than 10 minutes in water solution, and then it took around 860 minutes for urine solution. And due to the persistence of some pharmaceuticals in the urine solution, we required more than 10-fold higher energy to degrade these pharmaceuticals in the urine. So, going to the discussion part. So, as I mentioned earlier in the background section, this UV treatment has capability of degrading and inactivating enzymes through photochemical processes. So, this photochemical process can be divided into direct photolysis and then photooxidation. And due to the type of lamp that we used, it emits UV light at 254 nanometer and then 185 nanometer. And because of the lower wavelengths, we produce hydroxyl radicals. And from the results, we have observed that the inactivation as well as the degradation of compounds was less in the urine compared to water and synthetic urine matrices. But we have other radicals like hydroxyl radicals and sulfate radicals in synthetic urine and urine matrices, which can potentially enhance the inactivation as well as the degradation of compounds. For example, amino acid residue of tryptophan can react with carbonate radical as well as sulfonate radical with equivalent rate constant as to the hydroxy radical, and then the same goes for pharmaceutical compounds like diclofenac. So the lesser degradation as well as the inactivation in real urine might be attributed to the contents of the urine. And in order to depict this, we will develop a UV absorbance curve. And then in this UV absorbance curve, you will see solutions of urea over here in the orange line, and then ureas containing synthetic urine and water matrices, which are aligned together, and also urease spiked urine solutions. And then from this graph, we see that the absorbance increases whenever the wavelength decreases, and these UV lights affected synthetic urine as well as water containing urease subjected to UV treatment, where the absorbance increases, which entails that there are the degradation compounds of the urease as well as the other pharmaceutical compounds are formed, which absorb at different wavelengths. Whereas when you come to the urine, it doesn't affect the absorbance significantly, which entails that there is a shielding effect of contents of the urine, which can potentially reduce the effective light reaching the compounds of our interest. So this is the predominant photon emission wavelengths for the type of lamp we used. And the lamp also emits at 185 nanometer, but we couldn't measure this because we don't have the available instruments around here. So coming to the potential, we have seen that source separation of urine can reduce the pharmaceutical load by half, and then we can further minimize the pollutant load or the pharmaceutical load to wastewater plants by UV treatment by more than half. And extrapolating the amount of energy required to treat urine for a single household, considering urination volume of 1.5 liter and average person living in a single dwelling of 2.12%, we require an average of 220 watt hours of electrical energy per dwelling, which is equivalent with turning on two 15 watt lamps for about 14 hours. And also considering this UV treatment as a pre-treatment for urine dehydration, it would only add 4% of the electrical energy required to dehydrate or remove water from the urine. And then when you come to the challenge, there might be the survival of urease-producing microbials, so which might escape the UV treatment, and then such cases might lead to urea hydrolysis after the treatment during storage, long storage of urine. And then furthermore, it will be difficult to standardize the UV dose because there is no standard pharmaceutical consumption. For example, for dwellings which is occupied by elderlies, they consume more pharmaceuticals compared to youngsters or healthy persons. And since, as I said earlier, most of the pharmaceuticals we consumed end up in the urine. And depending on the type of pharmaceuticals we consume, we might get up to 90% of the pharmaceuticals we consume in the urine, which leads to higher degradation, which leads to the requirement of higher amount of energy, depending on the type of pharmaceuticals that we are dealing with. And then the other challenge that we have observed during conducting the experiment was there was a formation of stains in the UV slips, which might potentially reduce the effective light reaching the compounds of our interest. So, in conclusion, UV treatment can reduce the organic micropollutant load in addition to the reduction of the load during source separation of urine. And then we can also recover the nutrients as the total nitrogen content of the urine is not affected. And the energy requirement is very low compared to other nutrient concentrating technologies. And we recommend future studies to focus on the degradation as well as the toxicity of organic micropollutants, because during UV treatment, we might not get full mineralization. So there might be degradation products which might be like more toxic than the parent compound. And such system needs to be treated in pilot scale so that we'll know how much effective it is in both inactivating the enzyme as well as degrading the pharmaceuticals. And also, since the UV treatment has the capacity to also remove pathogens, future studies are recommended to inactivate pathogenic organisms for source separated urine. And from the UV absorbance curve, we understood that organic contents or contents of the urine interfere with the UV light reaching to the enzyme or the compounds. So a reduction of organic compound might or is expected to enhance the system effectiveness. Thank you very much. Thank you. Yeah.
Thanks a lot for that presentation. Then I leave the word to the evaluation committee, and I don't know who will start.
Maybe Shall I start?
Yeah.
Is that good?
Yes, please.
Okay.
The
Good.
one that traveled the farthest.
Okay.
Yeah, the long distance travel prize.
Okay. First of all, congratulations to a really nice piece of work. I think you really filled a big research gap. The treatment of urine with UV. I'm not aware of a lot of studies which have been done in this field. Maybe it's a little bit unfair, but I really want to address one of the points that you mentioned for further research, future research, and that's a question about urease producing bacteria. Because I mean, in the end, if you remove the urease, which has been excreted to the liquid, but the bacteria is still there, you still will have urea degradation. But I was wondering, I mean, you have really long times for the UV treatment, I mean, up to 80 minutes or something. Yes. I mean, are bacteria still an issue? I mean, if you really, use UV for such a long time.
Yeah, so we followed up another study where we studied the inactivation of microbials, pathogenic microbials, which are not potentially urease producing, but then they're like pathogenic. And then with the 80 minutes of UV treatment, we get around 7 log reduction. Within, like for E. coli, for example, we got 7 log reduction within 20 minutes treatment. But then for gram-positive bacteria like Enterococcus, it took around like 80 minutes to get 7 log reduction. So we might expect such kind of degradation for urease-producing organisms also. But there might be a buildup of like microbial biofilms, which can interfere with the UV treatment. Yeah.
So this might stay one of the major challenges, the biofilm formation. Another point which I think might be critical, in your report you showed nicely that, I mean, basically you have 2 mechanisms. Yes. I mean, one is the direct photolysis, the other one is actually the production of hydroxyl radicals. Yes. And those hydroxyl radicals, they react with organic compounds, can be the micropollutants, but also the bulk organic compounds, but they also react with chloride, for example. Yes. I mean, that's the standard mechanism of electrochemical treatment, with BDD, boron doped diamond electrodes, you produce OH radicals, and then they produce the chlorine. Yes. Now, chlorine, we know that is really critical when you produce chlorine because it reacts with a lot of organic compounds and you produce the critical compounds, trihalomethanes and others. Yes. Do you think this could be an issue as well?
We didn't follow it up or we didn't measure any kind of measurements to confirm this, but already contains chlorinated compounds, organic compounds. So there is a potential, but then we don't know for sure.
Did you look at the degradation of organic compounds?
No, not yet.
Or the removal of chloride?
No, not yet.
Okay.
Yes, and then this is not in the scope of the study. Like we only focused on the pharmaceuticals and then the enzyme degradation. Yeah. But then there are like other studies. Yeah.
This might maybe be something to
look forward to,
because you might produce. I mean, you mentioned that in your report when the pharmaceuticals are degraded, you might have some byproducts or products which might be critical as well.
Yes.
But also those products might be critical.
Yes.
Chlorinated products.
Yeah, I agree with you.
Yeah. Good. Maybe. How shall we do it? Shall I just continue with some questions?
Yeah, go for a second, I would say.
Okay.
And then hand over, and then you can continue later.
I will stop at one point. Yeah. Another one, combination with other processes. So one of the big issues which you showed is the reaction with organic compounds, bulk organic compounds, creatinine, whatsoever. Yes. Do you think it might be possible, or what would you suggest as a combination of treatment steps? Because UV I think it's a really efficient way to remove pharmaceuticals. I mean, that's what you showed from the water, examples. But still, the high concentration of organics is critical.
Yes.
What do you imagine? How could this be maybe optimized with combining with other processes?
Okay, so I'm also taking you back to the microbial activation. So here we will see we combine the UV treatment with the addition of hydrogen peroxide. And then over here, you will see the combination of UV with the peroxide, and then this is the inactivation with the UV only. So you will see there is like a high inactivation rates for the microorganisms. And then previous reports which was conducted in coupling hydrogen peroxide with the UV resulted in more degradation of the compounds. So combining with the hydrogen peroxide or other oxidizing chemicals would be beneficial, but considering that there wouldn't be any kind of residues left after that. Yeah.
I mean, the combination of UV with hydrogen peroxide is also used in drinking water to produce hydroxyl radicals.
Yes.
I mean, you could maybe also use titanium dioxide. I mean, did you look into, I mean, this is more like a catalyzer.
Yes, kind of catalyzer.
Yeah.
So with the addition of hydrogen peroxide, we enhanced the formation of hydroxy radicals. So the more hydroxy radical that you have, the more reaction that you will have with organic compounds. So like when the hydroxy radicals react with the organic compounds, the light transfer for the UV would be easier, and then we would have like more degradation through photolysis. Yes.
Another question that came to my mind when it comes to UV, you know, you have the mercury lamps, which you also used in your examples, but since a few years we also have the LED UV.
Yes.
And, this might really push the whole UV technology forward because they're so much cheaper and they need less energy. When you think about UV LED and compare it to the mercury UV, what is this comparable? Do you think that UV LED could also be used?
Yes, that is the way forward, because in using the mercury lamps, they have these service lives, and then after that, they would be considered as hazardous waste because of the contents of the mercury. So it would be better to move towards the UV instead of like staying on the mercury-based lamps. Yeah.
What's about the wave? Sorry.
Repeat that now.
Okay.
Yeah.
Sorry. The wavelength.
Yes.
Do the LED have the same wavelength or?
So you can make the UV LEDs, like if you want to, like you can make them like to emit at specific wavelengths that you want, and then you can even like make them emit lesser than 254 nanometer, which we commonly know for inactivation of microorganisms. For example, so here you will see the list of wavelengths over here. So the common UV wavelengths for the inactivation of microorganisms is here, and then most of the compounds, like the organic compounds, absorb a lot less than like 250, predominantly with around like 220. So this is taken from another study. You will show independent absorbance, UV absorbance of compounds, pharmaceutical compounds, and then as you will see, most of the UV absorbance tends to be here. So if you can make UV lamp that can emit in these wavelengths, we might expect higher degradation. Yeah.
But the LED, they're usually at higher wavelengths. Is it 300 and more? But I mean,
yes,
there might be new ones which actually go down to
there are other
280.
new ones which emit at 220 something.
Okay.
Yeah.
Okay. Great. I think this would be the first part from my side. Maybe can I hand over to Johannes? Is that good?
Okay, thank you, Kai, and thank you, Natnael. I can agree with Kai that this is a really nice piece of work, and especially combined with very high-level analytics and statistical analysis that's here. I think this is a very good piece of work, and I enjoyed reading it a lot. Thank you very much.
Thank you.
You mentioned, Kai, a lot of these general, larger pictures, so maybe I'll dig into some detailed questions and perhaps some of the technical stuff, and then we can go around once more. And the first thing that I could discuss with you is actually the picture that you just showed about the UV visual wavelengths of different compounds.
Okay.
And in your study, you also checked the UV curve of urea.
Yes.
And now my question is that, what's your opinion on using UV light for urea treatment, either after a pre-treatment step or as such, in a way that you could, do you see there a way where you could target, for instance, into a certain wavelength level and try not to destroy any urea, which is in high concentration, and instead somehow target specific compounds or specific structures so that you could just target the organic matrix, including the micropollutants?
Oh, that would be difficult because, like, they have, as I said earlier, they have different functional groups, and then these functional groups respond to different wavelengths of. This would be easier to. Yeah. For example, this compound, as you see, this is like the highest UV absorbance, like at this wavelength, right? But it can still absorb UV with this wavelength. So each compound doesn't have, like, they have this area where they absorb the UV. So even if you didn't affect a specific compound that can absorb a photon at this wavelength, you can affect other functional groups over here. And then we don't know for sure those functional groups will lead to better urea retaining or better degradation. We don't know for sure.
When you are measuring urea on this scale,
Yeah.
it seems like the peak is at around 195
Yes.
nanometers. So considering the previous research that's done on this, for instance, with a lamp of 20 nanometers, do you think that will be more specific to organic compounds? If we consider urea to not be an organic compound, it's slightly different. It doesn't have these complicated carbon structures.
Yes, so it will absorb until 200, including 220, but the absorbance is like very less. But still, we can consider 222 like for the degradation of organic micropollutants, like without affecting the urea, because the urea, the highest absorbance curve, like the highest absorption is around 190 something. Yeah. So we can address both the pollutants as well as the enzyme, as well as the pathogens if you want to, without affecting the urea.
Would you see that have an effect on the energy consumption?
In the literature that I referenced, they used the same type of lamp, which required the same amount of electrical energy. So I wouldn't presume that it would add any energy compared to the UV lamps.
I guess what I'm trying to get an idea is that what would be your idea of using a lamp, let's say in 2020 or 2030,
Yeah.
and then we would have this very high concentration of urea that you don't want to destroy,
Yeah.
and all the energy that goes into destroying that is lost. And whereas if you use a wavelength that does only target the organic functional groups that are taking energy that's below that, so higher wavelengths, would that maybe be a more energy efficient idea?
That would be difficult. Like I don't have the slide to support this, but like each compound, they have different functional groups, and then each functional groups, the wavelength emission is associated with electrovolts, and then depending on the requirement of the specific volts, some functional groups like carboxylic groups might absorb it. And then if you increase the UV emission, or like if you decrease the wavelengths of the emission, phosphate groups might absorb it. So we have a number of functional groups surrounding a given compound. So you can't even like target it.
Okay.
So it would be difficult, like unless you studied by stepwise like identification of which wavelength is like best for the degradation of a given compound. It would be difficult, like what kind of degradation products are produced. And from this, graph, we could also understand that even if you emit like specific wavelengths, you can only destroy like a few number of compounds. So there might be another compounds which might be interest of you that would be still there. So that's why we recommend like addition of oxidizers instead of like UV, addition of oxidizers so that they would react with any compounds in the solution.
All right, thank you. Then I could ask maybe about your, this is maybe already quite a technical question, but about the use of electric conductivity as a measurement for both ammonium, and then from ammonium you're calculating the enzymatic activity.
Yes.
And I think this is a very nice way of getting a quick management, but do you see any problems or things if you compare it with the real urine and then synthetic or water? What could be happening? Do you think that the measurements are comparable? Is it only ammonium that is causing electric conductivity in the medium?
Yes, so in the control experiments that we conducted, after spiking urease, we only followed the total ammonium nitrogen. So urea being present and then spiking the urease, we only expect the increase in total ammonium nitrogen instead of like other compounds. But still, when you form ammonium, they're also bicarbonates, right? So they would also reflect on the conductivity. Yeah.
Yes, I think this is a nice way. In your work, you're talking about the electric activity, and how did you calculate the electric activity for point sources when it's a method of it's a measure of rate constant? Did you have a model going through? Okay.
We made a standard curve prior to conducting the UV treatment using the same urine solution. We add the urea spiked with 500 milligram of the urease, and then we develop a standard curve.
Yes, that's a standard curve
for each time point.
For the ammonium concentration, isn't it?
Yes.
Yes. And when you're calculating the enzymatic activity, that's the change of the ammonium concentration.
Change of conductivity, and then we measure the conductivity and then transfer it back to total ammonium nitrogen.
Yes, and if you have 4 points on the line and you're measuring the rate of change at each point.
Yes.
Are you fitting a curve to these points?
Yes.
But the fit that you're talking about is the fit between EC and ammonium.
Ammonium.
But then when you have the rate change of ammonium, am I making any sense?
What we have checked was...
So how you know the speed of change at one single point?
Because we tracked it through time.
Yes.
Yes, so let me go back to this one.
I'm sorry, this is a very technical question already.
Yeah. Yeah, over here, for example. Yeah, so this is the control experiments without the UV.
Yes.
And then we spiked urease enzyme. This would be better. Yeah. We spiked urease enzyme, and then we tracked the conductivity each time. So we will see the change in the conductivity, rate of change of conductivity, right? And then in the control experiments, which is this, we relate the increase in conductivity with total ammonium nitrogen. And then we have a standard curve, right? And then we will use this standard curve of relating the total ammonium nitrogen with the EC for the samples receiving UV treatment. And then we follow them using the same treatment time that we used.
In the graph here, you have the ammonium concentration.
Yes.
And in your article, you're showing the rate of change of this. So in order to calculate that, wouldn't you have to somehow model the curve of this so that you know the gradient at each point?
Yeah, that's what we do. Like when we make the curve.
But in the picture here, if you, for instance, follow the yellow line, how do you estimate the rate of change, for instance, in the top piece there? You know the ammonium concentration, but do you know how quickly is it changing at that time?
Yeah, as I said, like when we increase the treatment time, let's say we spike the urea and then urea, right? And then within 1 minute, there will be formation of ammonia. We measure that. After 5 minutes, we measure that. So there will be change of ammonia as well as conductivity.
Yes.
Yes.
Yes. Okay, I think we can leave this here.
Okay.
Sorry, it might. I also might be completely off. Then I had just one more question about the Black's standards of degradation of micropollutants. So when you run the reactor without any light in it, and then you saw degradation of pharmaceutical compounds, and there were some that were degrading quite rapidly also. How was that affecting when you're showing then the results for the degrading pollutants? That do you take that bias off from the results? So if one of these is degrading also without oxidation, are you like subtracting that degradation from the degradation that you see with the, or do you assume that all the degradation is due to the light?
Yeah, so one thing that we can for sure tell whether the degradation is because of the UV or not is by following the control experiments, which also conducted in the same photoreactor. Because you might expect some kind of like absorption in the walls of the photoreactor. So in order to avoid that, the control experiments were also conducted in the photoreactor, and then we will track the initial concentration of the pharmaceuticals that we spiked with the final one. And then if you get the same pharmaceuticals from the initial and then the final one, and then you only get the degradation because of the treatment, then you will know for sure it's because of the treatment.
So for the pharmaceuticals where there was degradation also without the UV, when you're calculating how much did you degrade due to the UV, do you take the whole degradation or do you take just the additional degradation compared to the blank?
The additional degradation.
Okay, this was my question. Thank you. I can maybe give the third person also a cycle.
And then just to add something on the last question that we have also seen degradation with higher standard deviation, and we also like highlighted that concluding any kind of conclusion regarding the degradation of compounds, such kind of compounds might be taken into like consideration, because this might not reflect the real degradation because of the treatment.
Compounds, you mentioned in your presentation you started 150 compounds or more than the 150, and then you end up in the 75. And when I checked these quite extensive the compounds, I couldn't find any painkillers. Are they in the first round and you somehow excluded them, or why you, for example, paracetamol, it is the much more common compound that you can maybe find, or ibuprofen?
Yes, we agree. It was present, but it didn't pass the analytical criteria, because when we do the LCMS measurement, we also follow calibration curves, and then whenever it is way over these calibration curves, we will exclude it. And then the other one is the recovery, because if we didn't recover enough of it from the urine, and then we cannot conclude whether the degradation is because of the recovery or because of the treatment. But it was present. Painkillers also. Yeah.
Also, I mean, you focused in the first paper mostly the total nitrogen and the urine, but my question: have you considered about somehow byproduct formation, like, because there are organic compounds as well. We don't know what they are, but for example, like the nitrosamines or others, I mean, some byproducts can be much more toxic and dangerous for the environment after the UV treatment.
Exactly. Yeah, exactly. That's why we recommended that further study, like the next study, should be followed by investigating whether there is more toxicity than the parent compound or not. And then there is another study which studied such kind of cases, and they reported that some of the compounds might even incur more toxicity than the parent compounds.
But is it for the organic, these pharmaceuticals and the other things? So my question much more the nitrogen based compound.
Exactly. As Kai also mentioned earlier, chlorinated amines might also be produced within the treatment, but we haven't measured them. But they have like more adverse effects than the pharmaceuticals.
Okay.
Yeah.
Also, I mean that when you were measuring the total nitrogen, I mean, somehow have you considered the mass balance to transfer all the the other nitrogen types, not only the byproducts also? Have you considered to make at least the characterization in the first stage?
No, we haven't made any characterization, but we try to explain the urea oxidation, and then what we have seen was an increase in nitrates, which can be seen in here, like at 222, around 222 nanometer wavelengths. But the increase in nitrates and nitrites doesn't reflect the amount of nitrogen we lose, the amount of urea oxidized due to the treatment. But since one of the intention of recovering the nutrient was also to produce a valuable fertilizer, we don't want to lose any kind of nitrogen. So what we were interested in was to have the urea nitrogen as it is as possible, and also removing the rest of the compounds like pharmaceuticals, and then also inactivate the enzyme. Our whole intention is focused on the nutrient potential of the urine as well.
Okay, thank you. And for the enzyme part, you focused the EC to reflect the enzyme activity, but what
Yes.
are other methods? So when you think about the assay, do you think that the EC-based method is sensitive enough to make such a characterization or the analysis or approach, or do you think it can be assessed by the other assays for the urea's activity? What are the other assays you can?
So in this experiment, we used extracellular urease, like just to say, because we used JAK-pin urease, but one of the other reasons that urea hydrolysis was due to microbials which produce urease. So we can also follow the inactivation of such microorganisms. But using the conductivity is like very fast, and then you can track whether there is hydrolysis or not, like right away. So, and then it would be applicable for household settings, or like for central urine storage tanks or urine processing facilities. Like it would give us like real-time change in concentration of urea or formation of ammonia. But we can also do it with microbial inactivation studies. But it will take time also.
Okay, and my last question is about these organic micropollutants. You also mentioned, I mean, we also discussed a couple of minutes ago about their metabolites and the transformation products, and we already know that some of the transformation products are more toxic, as you mentioned, than the mother compound. As far as I understand that you couldn't focus to that part, it's another study, of course. But when you consider your 75 compounds, based on the literature, do you know some of them has the much more toxic compounds? If you make, it is somehow like a heat map to show that which compounds, transformation compounds, are much more toxic after the UV treatment. Do you have such a literature survey, or maybe you could consider later? I don't know.
Yeah, I think I referred one paper which investigated the toxicity, but I don't quite remember what type of pharmaceuticals were there. But we also included one or two metabolites. Metabolites, like, for example, if you see over here, we checked pharmaceuticals with metronidazole, and then we also checked its metabolites, which is metronidazole with hydroxide functional groups, and then we see degradation in both of the compounds in the urine. So, which also shows that the metabolites could also be degraded because of the treatments. But since we didn't follow such methods for every compound that we tested, we cannot tell for sure. But as you said, there is a literature which says more toxicity can be incurred due to the treatment for some compounds.
Mm-hmm.
Yeah.
So maybe the transformation product should be much more on the focus in such application than the model compound.
Yes.
So, yeah, I mean, this is my specific question, but I have a general question. So this is your first 2-year study. I don't know if you will continue for the PhD next 2 years or not, but if you plan a future approach for that, just to put on this information knowledge, I know that you have some suggestions for the future, but for the next 2 years, if you have a chance and no limitation in terms of the instruments, budget, and so on, what is your priority to develop such a approach for the nitrogen recovery?
So the main targets for the source separation as a whole is to recover the nutrients and then also avoid contamination of aquatic environments because of these nutrients like nitrogen, phosphorus, and potassium. Even if phosphorus can be retained much more than the nitrogen in wastewater treatment plants, the nitrogen could also surpass the treatments. So the main idea for source separation is recovering the nutrients as well as stopping the environmental impacts because of these nutrients. So our main focus would be maintaining the nutrient potential as well as removing pharmaceuticals as much as possible. So in this thesis, we presented UV treatment, and then we also recommended combination of UV with other oxidizers. So we should follow up the study with trying with other oxidizers so that we would get like more degradation products for the organics as well as the pharmaceuticals by keeping the nutrient potential intact. So my way forward would be that one. And then maybe I would add removal of pathogens as well, because that's the concern when using urine-derived fertilizers. But previous research showed that we can also inactivate pathogens within a number of concentrating mechanisms, because the technology that I brought over here is a kind of pre-treatment. So we can use other urine concentrating technologies so that we recover nutrients, remove pharmaceuticals, and then finally get the end product that we want.
Okay, thank you so much.
Yeah.
I'm done.
Thanks a lot for this digital input, and it worked. Well, it's time for another round.
Yeah, let's go. You don't have questions? Or?
No, I'm not allowed.
You're not allowed? No. Okay.
You should be quiet.
So if Björn is not allowed to ask questions, maybe we continue here. Now, when it comes to, you said this is a pre-treatment, you just mentioned that. Could it be used as a post-treatment?
Yes, but
And what would be the advantages and what kind of treatment train would you imagine?
okay, so if you are really interested in using oxidizers other than the UV, then concentrating the urine would be concentrated urine would be beneficial because the amount that you would add might be less. Because over here you have like fresh urine with 95% water in it. But then if you are considering UV treatment, whenever you concentrate it, the transmittance of the solution like minimizes, which challenges the treatment of the UV as a whole. Yeah.
Because usually UV is used for drinking water,
Exactly.
or let's say as the last treatment step in wastewater treatment.
Yeah.
So,
but for the urine,
yeah,
like if you concentrate it furthermore, then you would get concentrated nutrients as well as concentrated organic compounds. So there wouldn't be any assistance with the water to help the UV for the transmittance of light. But if you are considering other oxidizers other than UV, hydroxyradical sulfates, persulfates, and as such, you can degrade the pharmaceuticals by keeping, like mostly, you can keep the urea, but there is a possibility of losing the urea as well because we're adding oxidizers, and then they don't select compounds.
So the basic goal of this is that you always want to keep the urea.
Yes.
And that just limits your possibilities of treatment steps that you can do. For example, if you take nitrification,
Yes.
then the urea is basically gone, and then after all the treatment steps, and maybe after the degradation of the bulk organics, you could have the final step of UV disinfection. It might be really efficient.
Yeah, that would be really good because for the nitrification, you remove most of the organics as well as you produce ammonia, right? But the recovery process next to this treatment might affect how we see this treatment.
Mm-hmm.
If you see nitrification, then it has to come after nitrification.
Mm-hmm.
Then we would have like very clear liquid, and then the UV treatment would be like much more effective.
Mm-hmm. Clearer. It's not very clear. But maybe another question which also relates to different treatments in some way. You know, you did your calculations on the energy demand, and you also showed it in your presentation. When you compare it to different steps, it's rather low. But you can also compare it to the current wastewater treatment that we have, and there it's more or less 4 watt per person. I mean, it always is different where you go. And this ends up to 90 to 100 watt hours per liter or kilowatt hours per cubic meter. In the end, I mean, this is really close to what you use for degrading the
organics.
The organics, and especially those pharmaceuticals. And I was wondering, I mean, one aspect could be the UV, and you showed that as well. In one example in the beginning, the urease was much more active when you actually treated it with UV. And the reason for that was actually the heating. So the temperature went up to 35 degrees in your reactor.
Yes.
You know? I mean, would heating be an alternative to UV? I mean, because this was one of the side effects. With UV light, you heat the liquid.
Yes.
And just heating it, I mean, the energy demand would be lower if you just heat it up to, let's say, 60 degrees Celsius.
Yes. So one way to address this is that, like, whenever we consume pharmaceuticals, our body temperature is around 37, right? And then they end up as parent compound as we take them. So you may see that like temperature doesn't affect most of the compounds. Instead, the metabolism is the one which is like degrading the compounds. And then after they are released from our body, depending on the design of the compound, some of the compounds might be like very degraded very fast. We can even use like solar collectors. We can even that doesn't necessarily require like higher UV emission light. But some of the compounds they can persist enough you can't remove them with more than 90 degrees centigrade. So it's like where to focus and which pharmaceuticals are present in higher concentrations, which are relevant from the environmental perspective. Yeah.
So getting back to the heat, I think heating might help to degrade some of those pharmaceuticals, but especially it might help to prevent the urea, the biological urea degradation. Would you agree with that?
Come again?
You know, I mean, you looked at two things. One was the pharmaceutical, the removal of pharmaceuticals or degradation. Basically, it's a degradation. And then also the urease, that you want to prevent that urease will actually degrade the urea. So I think the heat treatment, which I just suggested, could solve the urea degradation problem. Do you agree with that? Or
with the heat, I also referred to one literature saying that combination of heat treatment with stabilization could lead to urea oxidation. So, like, it wouldn't be like we have to find this, we have to do this optimization where we will have more degradation because of the treatment, but also keep the urea. And urea, its degradation temperature is way above 100 urea only. So it's like optimizing. And also, when we heat it, there might be loss of water, right? So those compounds, those pharmaceutical compounds which persist heat treatment, we might find them concentrated. So it's like finding the optimum condition over there. Yeah.
Okay, so maybe I hand it over to you, Hannes.
Thank you, Kai. I think that this was an interesting conversation because I think we are looking at the problem from two different ways of treating the water and keeping the nutrients.
Yes.
So the process here is getting everything. You're just removing the water, whereas the conventional thinking is that we are removing everything from the water. So it's a different one. Thank you. Maybe I can go. I have a couple of a bit technical questions, but we can go through them. We don't have to dwell too much. One question was that when you were designing this setup where you're using water and then you're using the synthetic urine recipe that doesn't have any organic components in it, and then you're using real urine. What's the research question that you aim to answer with this salt water that doesn't have the organics in? What more information have you pulled out of this and why was it selected?
Okay, so the idea we had was previous researches, as I mentioned in the research gap, for the uracil activation were done in water and then phosphate buffer solutions. And then this having synthetic urine doesn't really reflect how the enzyme or how the urate is hydrolyzed, how the urea is hydrolyzed in real urine. And then by having the synthetic urine, we will know for sure the effect of salts compared to the water. And then by including the urine, now we know the effect of organics in addition to the salts. And then with the UV absorbance curves, we clearly show that like there is the effect of organics. Yeah.
So the effect of the salts was shown when you were showing the energy or the time length required for complete inhibition of the urease enzyme.
Exactly.
And it was so that it was slightly longer for water, was it so? No, for
water.
For water.
Yes.
And so your conclusion from this is that the salts do help.
Not the salts, but because of the salts, we produce radicals other than hydroxyl radical, like sulfate radical and the carbonate radical. And then as I showed in this, they have comparatively the same, they can react with comparatively the same rates with amino acid residues as well as the pharmaceutical compounds.
Thank you. I think this is an interesting piece of data that also kind of gives some background to the physical processes that are happening there.
Yeah.
Then I had another question. You had performed an interesting study on the organic structures of your 75 micropollutants. but we don't see too much of those results. You said that you used a software where you modeled the different functional groups of at least some of these.
Not modeled, but
Yeah.
we try to identify like what kind of major functional groups are present in the pharmaceutical compounds. Yeah, let me take a, yeah, these ones. I don't know whether it's visible or not. Yeah, so those which are assigned with positive, they contain functional groups which are photosusceptible. And then I try to correlate the degradation of the compounds in the urine with the presence of these functional groups. And then we didn't find any correlation. But what I have done in the thesis was just to find out like what functional groups, photosusceptible functional groups are present in the pharmaceutical.
Well, if we have a hypothesis that there is a functional group that we know is light activated, and now we don't see any correlation with the degradation, what kind of conclusions are you drawing for this, or is there just not enough data to?
Not enough data.
Okay.
Because here you will have like functional groups, and then as I mentioned earlier, these functional groups respond differently to different wavelengths. And then we only studied like two wavelengths predominant two wavelengths. So we cannot say for sure these functional groups is more susceptible than this one. Yeah.
Okay, thank you. Well, I'll ask one more question and then we move on. And this one is maybe more about the results and errors in your results. You're presenting your results in a way that you're saying that for urine you need 50 times more energy or 90 times more energy compared to if it was just water.
Yes.
What do you think if you were to repeat the experiment and do a kind of a sensitivity analysis on your results, would you see the same results coming out if you were to run the reactors again?
Yes. With the follow-up study where we studied the inactivation of pathogens, we used a different lamp, but we found that no urea was oxidized, unlike this one. So we have seen somehow different results when it comes to the urea oxidation. But if we are going to redo the experiment with another urine, there might be higher or lower degradation depending on the physical chemical characteristics of the urine. If there are like more organics present, there would be interference as well as scavenging. So it depends on the type of urine that we have. But we will expect like fair amount of degradation, just like that we have over here.
Well, let's say that you do exactly the same experiment. You might have a different urine, or even if the exactly same urine, but you fill the reactor again and run the reactor setup. Would you get 52 times energy consumption estimate? Or do you expect that to be something else?
Yeah, it will be consistent because for the urea study, we used urines for 3 days, like different urines, and then we found comparatively the same results.
So you did the study 3 times, or you sampled the same study?
No, like using 3 different urines collected at different days. So which would represent like the different organic contents and the matrix as a whole.
So when you show those error bars and you have triplicates, that is the error bars for 3 separate days, 3 separate 80-minute oxidations.
3 triplicates of the same treatment.
Well, how about these 3 different urines then?
So we followed that one up, like just to make sure whether the results are consistent enough.
So if you show me one of the result slides which you have error bars in, for instance, the inactivation of urease.
Yes, this one for example.
For example here, on the right side slide.
Very high, yes.
Here,
yes.
Are these 3 different days of 3 different urines and 3 different exercises of 80 minutes, or is this a single exercise of 80 minutes where you take 3 samples or divide them?
So we collected the urine and then divided it into 3 and then run it in the photoreactor independently.
Okay, so this implies that if you were to repeat it, we would assume to get very close because your error bars are very tight. I mean, the results are very accurate, even though it's, so if you were just running it once and measuring them 3 times, we could expect that the curve changes every day, but just the measurement is exact. But then these are, I think, more valuable results. You are expecting to see the same kind of thing happen even if you repeat it again. All right. So that was my question on the sensitivity, I would guess.
And then the same goes for the pharmaceutical study also. Like we conducted from the batch of urine, separate reactors like 3 times. And then we have like triplicates of the samples also, like from each treatment.
Okay, so you have 3 and 3.
Yes.
And these error bars, are these standard deviations of those 9, or are they standard deviations of 3 averages?
9.
9, okay.
Yes.
Okay, this is just good metadata, thank you. I think we can move on to next question, please.
Yes.
Yeah. What about you, Sinet? Do you have any more questions for us?
No.
Thank you. Then, well, I can come back to you, or should we perhaps, Åke, if you have any questions to add at the moment.
So, thank you very much, Natnael. It's very interesting, very nice presentation, and a very nice and interesting thesis. I am by no way expert in pharmaceuticals, their degradation and chemicals and absorption patterns and things like that. But as I get it, you are using this UV treatment as a kind of a multi-purpose thing. You like to maintain the urea, you like to degrade these pharmaceutical OMPs, and you want also to avoid growth in the pipes in a way. So metaphorically, it's a kind of a treatment kinder egg, you could say. I had that question, which already had been addressed, and looking at it, is it possible to combine it with different treatments or see it as a pre or post treatment or additives? Because you mentioned, I think it was citric acid in your thesis, and also with peroxide, for example. But we can skip that. Let's go to, you had a conceptual picture of the urine diverting toilet and the pipe.
Yes. This one?
Yeah, that's one. I was just thinking from the work you have been doing now in laboratory scale. You have been using a certain kind of pipe dimension and a certain length and also diameter of the UV lamp. Do you think that those aspects is something which is important also to kind of elaborate more on? I understand that the energy requirement is of course vital, that you should not exceed it too much, but is there anything which has to do with the kind of the volume between the UV lamp and the outer part of the pipe, which could be important to consider?
Yes. So for the UV light to be effective, the sample has to be within 1 centimeter range, and then we will get most out of the 185 nanometer. But then the 254 nanometer can pass through like until 50 centimeter.
Okay.
So what we have proposed was to have such kind of configuration where we would collect the urine over here next to the toilet, and then we would have a flow stabilization tank or flow stabilization chamber to the left, and then we would either dry or stabilize the urine like in the next chamber.
Okay. So
and then we need to figure out somehow like the size and everything to fit over here. Yeah.
So will you then have some kind of, I mean, in the study you did, you had also circulation that you were in order to kind of then also have the contact for a certain period. Will it be the same thing in a kind of application that you have to recirculate the urine in order to have the efficient treatment, or is it like just one through the pipe, or?
Like every time, like from the process perspective, like mixing is necessary so that you would have like more exposure of the compounds to the UV, as well as for the enzyme. But then it would become like, if everything is stagnant, it would become very challenging when it comes to the stabilization.
Yeah.
Because whenever the microorganisms inactivate, they form kind of flock formations, and then some microorganisms might be protected by this flock formation from the UV light, and then there might be formation of biofilms in the walls of the photoreactor.
Yeah.
So always recirculation is better
necessary.
to have.
Yeah.
Yeah.
So even if you are looking at the kind of pattern when people are going to the toilet, where there's a kind of a loading to the system with it, you still need to recirculate and expose in the tank in order to avoid the growth of the microbes and
Yes.
the urease.
But we can use pressure differences so that we would have like some kind of mixing.
Yeah. Thank you. And the next thing, you also mentioned in your discussion here that you compared it with a previous study using wastewater, and also saying that you needed tenfold more energy for removing the OMPs in the urine. Is that based on, I mean, wastewater is of course very complex also, and it can also be very different in different concentrations. But is this, and you also, I mean, you show that it's more concentrated, so from a volume perspective, it's just 1%. But I was thinking, is this due to that, I mean, as I see it, there is a lot of kind of the energy, you also have organics, which is kind of parasitic use of the energy in relation to what you like to achieve. But is it due to the higher concentration then of the organics, which means that you have a tenfold more energy demand for the urine compared to wastewater?
Yes, because the energy demand required for inactivating and also for degrading compounds was very low. Like in water, for example, we achieved more than 99% degradation within 10 minutes of treatment.
Yeah.
So it's only because of the organics presence in the urine that made this high energy requirement.
Yeah. Okay. Yeah. Thank you very much. Thank you.
Thanks. Are there any questions remaining?
Maybe one last, if you still have time.
We have plenty of time.
Good. Actually, this question is really a follow-up of our discussion, because and this is really to pick your brain on all your experience with those experiments, because something that came out for me is it might actually be more a chemical reaction, like hydroxyl radicals, maybe chlorine or something else, than really photolysis.
Yes,
so that might be, and I think this is a really nice outcome to understand this, because this might also open the door to, okay, do we need UV or should we add chlorine directly? Yeah, how we could really identify whether this was like the hydroxyl reaction.
Yes, so I made a table saying, reflecting how much of degradation is present because of the UV and then because of the indirect oxidation. And as I said earlier, their response towards this treatment depends on their photochemical property as well as their reactivity. So it depends on the compound. You may say that like this compound degradation is mostly because of the photooxidation or because of the photolysis. When you come to the diclofenac, for example, Yes, compounds like this. Compounds like this, they are very photosusceptible. So you might expect very high degradation. And then for compounds, for the same compound in the urine, it's because of the presence of the organics, it took much time, right? So you may say that this compound is highly photosusceptible, but still the degradation is like somehow retarded. Did I get your question right?
Yeah, and you also, I think so, yeah. But I mean, you also did this comparison with the properties of the different compounds, how susceptible they are actually for photooxidation and so on. You know, what I'm heading at is what kind of experiment would I have to do to really differentiate between photooxidation and
You have to study
I call it hydroxyl radical oxidation. What kind of experiment could you do to really find out whether in urine, in pee, or that the other is more dominant?
So you have to study them independently, but there is already literature available. And in the literature, they say that like, in order to see whether degradation is occurred because of the UV treatment, instead of studying all these compounds, we have to focus on these compounds instead, because they are more of interest, because these compounds persist enough the treatments that they have already passed through. The rest of the compounds have degraded enough so that there wouldn't be any concern.
Okay.
And then you study these compounds persistent enough, and then you have to study them independently. But as I told you, there is literature available already. So it wouldn't make any sense to study them like in the urine, because after all, their degradation would be the same.
I think it's a lot about scavenging.
Yes.
You know, whether either the light is scavenged by the organic compounds or the hydroxyl radicals. So maybe with scavenging, something could be done. Or you could, I mean, there are specific probes that scavenge hydroxyl radicals. Or maybe this goes in the direction that you do on the right side as well. I mean, it's really, you could choose one pharmaceutical which is really susceptible to photooxidation, and then just look at this one, and then maybe also, this was really just brainstorming. Maybe I might go back to the lab and do some of those experiments.
So just to reflect, to add more information, carbamazepine was one of the interests to look at for wastewater treatment plants, because it is persistent enough for every treatment. And then we also found that this compound is persistent for the UV treatment also, in our case. But in the urine, we were able to degrade it with more than 99%, like with more around 99%.
Okay.
It's still degradable, but we need more optimization to increase degradability in the urine and then wastewater matrices. Okay. And then maybe there might be some. So each compound, they have this KFC where they relate the soil absorption coefficient. So these compounds has the ability to attach themselves to particulate matters, and then whenever they do that, their functional group would be shielded, and then also wouldn't get any kind of effect out of it. So there are like a number of properties of the pharmaceutical that we need to consider, but still increasing the hydroxyl radicals or oxidizers might be the way forward to go.
Okay, thank you very much for the answer.
Thank you.
Yes, thank you. I can also give one last question, and that relates to your UV study in context of urine source separation. And I know that the group here has been doing several different technologies to look at how do you stabilize the urea, because a lot of the previous technologies always first degrade, or simultaneously in organic systems you degrade or let it degrade, and then you're working with bicarbonate and ammonia and see what happens. But your focus is on keeping it as urea all the way to the fertilizer, and urease uses directly as a fertilizer.
Yes.
And you have these different methods that you've been studying to stabilize urea. So how would you compare these systems, different adding chemicals, using, for instance, these resins or other methods of changing the pH, and then comparing to urea? If you don't consider the destroying of organic compounds, but just stabilizing the urea, how viable is it? Would you go with the UV, or would you go with something else, or would you go with the combination?
So I haven't made any comparison with the other technologies, and but you can use criteria such as whether the urea is present or not, and based on the organics removal, and then also with the energy demand, and then its applicability to fit either household setting or decentralized setting. So you can use these criteria to select among the available technologies. You can stabilize by chemical methods, electrochemical methods, and then this one is an alternative now. So you can differentiate which one to use based on this criteria, but I haven't made anything, so I cannot tell for sure.
If you had to give a gut estimation right now, what would you say?
So the gut estimation would be using the chemicals, because their cost is very low compared to the energy demand that we see over here. So going forward with the chemicals would be good. But the advantage of this treatment is, in addition to the inactivation, it also gives you degradation of micropollutants.
With the chemicals, let's say that we stabilize the urine using chemicals and we have it in either low or high pH. Would you imagine that there would be any effect on the pH to UV treatment? Would some of the chemical forms, for instance, change in the organic matrix?
Yes. So one thing that would change would be the pKa for the chemicals, and then whenever the pKa of the compounds change, their functional group might be available for reactivity or might be stable enough. So depending on the pH, we might get higher degradation or persistence, but it depends on from compound to compound. Yeah.
Thank you.
Thanks a lot. Then maybe the time for asking for all of you. Are there any more questions? Eski.
I should congratulate you for the wonderful thesis, and also I really enjoyed the presentation and the discussion. I'm very happy for that.
Okay.
And I'm away from the subject area, but I have some questions, general questions. But if you see your thesis, and just like PV, pH, or like that, some abbreviations are standard and known, but on your very title, you use the UV as a beginning.
Yes.
And even if it is very short, you couldn't use it ultraviolet based, like that.
Yes.
To make it easier for the readers.
Yeah, that would be wise, but there is this thing that for the title, it should be within 20 words.
Yeah.
So we try to fit in everything to maintain that.
And then I think we discussed also the energy related. And at the end of the result, you say that energy consumption is high, which is as I understood you. But in your discussion and the conclusion, and it is better than other technologies like that. So in order to reduce this energy consumption, do you recommend any supplementary to your approach?
Yes, that is the thing that we were discussing before. If we add oxidizers, for example, it would react with the organics, and then whenever it reacts with the organics, the color transparency of the urine would increase. Even if that we didn't provide it over here or in the thesis, we followed the urease inactivation by the addition of hydrogen peroxide. And then we observed that the light transparency increased right away. Like once we dosed the urine with hydrogen peroxide, it becomes transparent, and then leading to almost half of the treatment time required to inactivate the enzyme in the urine. But since there were like issues with the data, we didn't present it over here. And then, as I said, we would add catalyzers or oxidizers to enhance or reduce the energy requirement.
And in your conclusion, you said that all the pharmaceuticals, around 50% are removed, is it?
Yeah, because of this treatment only.
Yeah, because of this treatment.
Yes.
Are there any special pharmaceutical compounds or elements which you identify which not removed by this method?
Yeah, so as I said earlier, carbamazepine and also metformin. This is the blood-lowering agent that we took, metformin, and then these compounds were like persistent enough throughout the treatment. And some psychoactive, this carbamazepine is psychoactive compound, and then it would affect other organisms. And then if it reaches us, it's like we are taking medications that we don't need to. So there are some compounds which are persistent enough that we need to take care of.
Yeah, the last question, this another. In your gap, you say lack of standard pharmaceutical consumptions. Yes. So in relation to the people settlement, urbanization, I think this is the future. This
yes.
Like that. What do you think on the standardization aspect, how you can manage that one? You need
of course we need
research on that?
Yes,
or,
of course.
Yeah.
Yeah.
Okay. Thank you very much, and congratulations once again.
Thanks so much.
Thank you. Any more questions?
And then just to reflect more upon the last question, I also provided with the pharmaceutical consumption in Europe as well as in Sweden. And then through the years, we have observed that there is an increase in pharmaceutical consumption, which would show you that there would be an increased complexity in the urine matrix to deal with. So this also provides, this will become a challenge in standardizing the UV dose.
Okay. Thanks, Natnael. Very interesting presentation and discussion. So I am also still a bit stuck on this, whether you should use the UV treatment or chemicals. But if we were to use only UV treatment and really go for the catalytic impact, you would have to have a number of different wavelengths, right? You couldn't just go with one, right? And you said that you would have to study them independently to decide which one has what effect. But how could you do that? Because when you do form the free radicals when you shine with the UV light, right? So how can you study only the photocatalytic effect without the impact on free radicals?
So in the literatures, what they have done is they would add oxidizers that they know of, and then they have this rate constant of the reactivity of hydroxy radicals with the compound. And then now they will subject it to the UV. So the difference between these two, you would get whether the pharmaceutical is degraded with the addition of radicals or oxidizers, or because of the UV only. And then also you add scavengers for the hydroxy radicals that might be formed during UV treatment. So let's say you have UV treatment over here, right? So during UV treatment, you might produce hydroxy radical, as I said before. So you'd add the pharmaceuticals, and then you would add scavengers for the hydroxy radicals to be formed. And then you would know exactly you would get the degradation because of the UV only. And then you would do another experiment, leaving alone without any addition of scavengers. And then you will do another one where you would add oxidizers. So between these three, you would get clearly the effect of hydroxy radicals in direct degradation with the photolysis.
Could you not also study the absorbance of the compound in interest before and after UV?
That
radiation?
you would do, but the problem is here is that, as I showed here, yeah, so when you do the molar absorption, what you would get is an absorption, list of absorption for different wavelengths. So if the type of UV lights that you are employing doesn't fit to exactly to the highest molar absorption coefficient, you might not expect better degradability.
No, but if you're studying a specific compound, you should be at this
Yeah,
specific
instead of
wavelength.
molar absorption, you should rely on quantum yield. Because quantum yield tells you that how much amount of the compound of your interest is being responsive to the amount of photons absorbed.
Okay.
Yeah.
And then it was this, because I know we have discussed this before, but I'm just wanting to hear if you've thought about it a bit more, whether it in any case this treatment would be bad in the case where you don't actually have any pharmaceuticals or have very low pharmaceutical concentration. Would this treatment actually be worse, or?
Yes. Zainab also mentioned that one, and Kai also brought it up. Chlorinated amine compounds. So if there was no pharmaceuticals present, we might also activate chlorines, which is found in the form of salts in the urine. So this might lead to creating compounds which are adverse effects.
Because also you said that there are some more persistent compounds, and if you have them, you would have to have a more intensive treatment, right? So
Yes.
and then you have to standardize it. So you have to kind of assume that you have some collection of compounds and then standardize the treatment for that. But is there any case where you would want to have a lower grade, or how would you standardize it? I just curious about that.
It's so difficult because in the wastewaters, you would get fairly good idea of
Yeah,
how
but
much amount of...
you're suggesting household.
Yes. But for the wastewater, you get fair idea. But for the household settings, you wouldn't get anything because you might be healthy sometime and then you might be sick sometime. So it would be difficult to get the standard for. So instead, this would lead us, instead of treating the urine at household settings, it would be better to treat it in decentralized form, where we collect the urine from households and then treat it in the decentralized treatment sections.
But then you couldn't do the drying at household level. Complicated. Thank you.
Yes.
Thank you. Any more questions? Nothing digital. Okay, thank you. Then I think it's time to close this thing. And first saying that there will be a closed meeting up on the 5th floor of this house, and there will be time for you to wait for a decision outside. And then a lot of thanks to all involved on the evaluation committee, of course. Okay, with that, then I will close this session. Thanks a lot.
Thank you very much all. Thank you, Mr. Supervisor Committee. Thank you very much.